Welcome to our series on Counting to Calculus, a historical perspective. I'm going through the book Journey Through Genius, where we're going to start from the beginning of math history and work our way down in understanding how we've gotten to where we are today in some of the theorems that people are working on in mathematics around the world. My name is Amos, the math guy, and I believe that math is one of the most beautiful fields of study and that it is gettable, and I take it seriously, and I want everyone to learn math well. So we're going to talk about mathematics now. Before I dive in further, I've written a book called Tools for Master Mathematics, which I will be more than happy to send to you, a free copy through the PDF version. But basically, I teach students how to do math well. I use principles of deliberate practice discussed by Dr. Anders Ericsson in his book Peak. He's the one who did the 10,000 hour rule study. So we have math curriculum for elementary school students. We use Singapore math, and we also have other math curriculums that we use. We help students to master mathematics, have a solid foundation, and we also have a middle school math curriculum, a high school math curriculum, all the way to calculus. My students are able to get 21 credits of math before they graduate high school. I help students get up to 60 credits of math and history and English, and we have a partnership with a university that helps us with that. So reach out to Amos, the math guy, at gmail.com if you're interested in my dual enrollment program or in just becoming very good at math. And even if you're the best in math in your country, I have some tools to help you even go up to the next level. And if you hate math and you just think it's terrible, reach out as well, because math is beautiful. We'll do what we can to help you enjoy the journey. So we're going to start from the beginning here, and then I'm going to read from another book, just a quick set of quotes. Our knowledge of the very early development of mathematics is largely speculative. Now, we will focus on a specific civilization that had math well, and that civilization is in Egypt. So we have Egypt right here. We're going to talk a little bit about the Egyptians today. So we piece together different parts of archaeological fragments and architectural remains, and we make educated guesses. The invention or the focus on agriculture is part of the beginning when we talk about mathematics. Humans had to address this, right from the beginning of time. We have Adam and Eve, we have Abraham and Job, and different stories in the Bible you hear about. And it is important to note that even at that time, right, they were learning about patterns and the Nile River and studying its behavior, right? People were already scholars right from the beginning. And then, of course, the pyramids, which came after. But let me not get ahead of myself here. So humans the two most fundamental concepts of mathematics that they had to deal with was multiplication or multiplicity and space. The notion of multiplicity or number would arise when counting sheep or distributing crops over the centuries. Refined and extended by generation of scholars over the centuries, these ideas evolved into arithmetic and later into algebra. The first farmers, likewise, would have needed insight into spatial relationships, primarily in regard to the areas of fields and pastures. Such insights carried down through history became geometry. From the beginnings of civilizations, these two great branches of mathematics, arithmetic and geometry, would have coexisted in a very primitive form. This coexistence has not always been a harmonious one. A continuing feature of the history of mathematics has been the prevailing tension between the arithmetic and the geometric. There have been times when one branch has overshadowed the other, and when one has been regarded as logically superior to its more suspect counterpart. Then a new discovery, a new point of view would turn the tables. It may come as a surprise that mathematics, like art or music or literature, has been subject to such trends in the course of its long and illustrious history. Now, here's the cool thing about math, though. If something is proved to be true in math at one point in history, that stays. If that is true, math and logic are closely related. As a matter of fact, logic is the very basis on which math then rests on which physics then rests on which chemistry then rests on which everything else rests on, right? So there's a pattern to this. We have logic at the very bottom. And then we have math. And then we have physics, and then we have chemistry, and then you have biology and other fields of study, right? But notice that the first four levels are logic, math, physics, and chemistry. Physics is fascinating, and I think part of it is that there's some mystery to some of the principles in physics that just blows your mind. Black holes and conversations about space-time and all of that, right? Veritasium just did a video about, about Einstein's equations and the black holes and World War I, and I love how he put the historical perspective into everything. That was really cool. We find clear signs of mathematical development in the civilization of ancient Egypt. For the Egyptians, the emphasis was on the practical side of mathematics as a facilitator of trade, agriculture, and other increasingly complex aspects of everyday life. Archaeological records indicate that by 2000 BC, the Egyptians had a primitive numeral system as well as some geometric ideas about triangles, pyramids, and the like. There's a tradition for instance, that Egyptian architects used a clever device for making right angles. They would tie 12 equally long segments of rope into a loop, as shown in figure 1.1, stretching 5 consecutive segments in a straight line from B to C, and then pulling the rope taut at A. They thus formed a rigid triangle with a right angle BAC, and there's a picture that is shown here for what they were trying to do. So they were able to create right triangles that way. This configuration laid upon the ground allowed the workers to construct a perfect right angle at the corner of a pyramid, temple, or other building. Notice that they were already talking about temples right in the beginning of time. See, humans seem to be curious about the questions of God and faith and the spiritual realm, right? That seems to be the case all through history. So that's interesting. By nature, people are elongated. And Solomon said this in the book of Ecclesiastes in the Bible. So anyways, I have a channel called Living Sensibly with Amos Tarfa, where I talk more about my faith and lessons from the Bible. Implicit in this construction is an understanding of the Pythagorean relationship of right triangles. That is, the Egyptians seem to know that a triangle with sides of length 3, 4, 5 must contain a right angle. Of course, 3 squared plus 4 squared is equal to 9 plus 16, which is 25. So we catch an early glimpse of one of the most important relationships in all of mathematics. Technically, this Egyptian insight was not a case of the Pythagorean theorem itself, which states that if triangle BAC is a right triangle, then A squared is equal to B squared plus C squared. Rather, it is an example of the converse of the Pythagorean theorem. That is, if A squared is equal to B squared plus C squared, then triangle BAC is a right triangle. Notice logic, converse. If a triangle, if you have A squared plus B squared is equal to C squared, you have a right triangle. And if you have a right triangle, A squared plus B squared will equal C squared. That's where the converse is happening. Okay. It's not always the converse is not everything can be put in that sense. Just because if this, then that doesn't mean that that equals this. Logic is important. And that's part of why in my STEM cubed equation, which I talk about on this podcast, we are talking about the importance of symbolic logic as a part of STEM. We need people to understand logic. So that is for the proposition of the form if P then Q, the related statement if Q then P is called the proposition's converse. But in the case of the famous Pythagorean theorem, both the proposition and its converse are valid. In fact, these will be the great theorems in the next chapter. Stay tuned for those equations we're going to do on the board. Although the Egyptians seem to have some insight into the geometry of 3, 4, 5 right triangles, it is doubtful they possess the broader understanding that, for instance, 5, 12, and 13 triangles, or 65, 72, and 97 triangles, likewise contain a right triangle. And you can prove it. Try it. 5 squared plus 12 squared, what's that equal to? And then 65 squared plus 72 squared, what's that equal to, right? That's for those who have time. So then he says, more critically, the Egyptians gave no indication of how they might prove these relationships. Perhaps they had some logical argument to support their observation about 3, 4, 5 triangles. Perhaps they hit upon it purely by trial and error. In any case, the notion of proving a general mathematical result by a carefully crafted logical argument is nowhere to be found in Egyptian writings. The following example of Egyptian mathematics may be illuminating. It is their approach to finding the volume of a truncated square pyramid. That is a square pyramid with its top chopped off by a plane parallel to the base. Such a solid is called a frustrum of a pyramid. The technique for finding its volume appears in the so-called Moscow Papyrus from 1850 BC.